Sure. Thank you, Dr. Ahmad, and welcome everybody to this webinar on the geothermal energy. My name is Ebrahim Fathi. I'm an associate professor at Petroleum and Natural Gas Engineering at West Virginia University. The major work that I have been doing since 2010 was on the unconventional reservoir development, especially on hydraulic fracturing and stimulation, which I published two books on those, which are presented here. And past 6-7 years with the new administration, new focus and attention to the energy transition, majority of my research and the projects are based on the carbon capture and CO2 sequestration, and also the geothermal. The big projects that I'm involved as an investigator is WVU geothermal deep direct use, which basically the idea is to investigate and explore the capacity of the Appalachian Basin here in West Virginia, specifically Morgantown, to see the possibility of using geothermal energy for direct use. We will go over these discussions and the definitions, what we mean by direct use, which is basically we wanted to use the earth heat to heat and cool the whole university. Currently, gas-fired plants are used to generate energy and use that for heating and cooling. So the idea is, can we transfer to the geothermal? So we drilled the well this past summer, and we collected all the information regarding the logs, cores, and we are evaluating both shallow formations for the heat storage and the deep formations for the heat extraction. The project is very unique because this is the first project in the US, I believe, that combined both geothermal and the CO2. The idea is to also store CO2 in the shallower formations, and we are investigating the possibility of using CO2 as a working fluid for increasing the efficiency of this heat extraction from these geothermal resources. And the other projects that I've been involved includes the carbon capture and sequestration in Citronelle, which is another field in Canterbury, and the other project is the Illinois Basin Decotter project, which is called generally they call it the IPDP. This is the bioenergy carbon capture and storage, which our part is again to look at the natural fracture systems and to evaluate the capacity of the reservoir to store CO2. And the big project which is coming and it will start pretty soon is called Tri-State CO2 Storage Hub Project, which is basically providing the storage hub for the state of Ohio, Pennsylvania, and West Virginia. A little bit of a paid advertisement. We are located in West Virginia University in Morgantown. We are about an hour and a half distance to Pittsburgh, and 3 hours and a half distance with the Washington, D.C. So going to our discussions, when Dr. Ahmed asked me to give this lecture on the geothermal, the original plan was to just start with the introduction of the geothermal and then go to the advancement and the technologies. But then I thought it makes more sense to start with building a basis for this discussion, for this whole discussion. We know the geothermal reservoirs and even application of that and then using that is not something new, right? The geothermal reservoir has been known, and actually investment has been done going back to 1970s, right? So we have like 1971, we have projects and investments on the geothermal reservoirs. So why now, like after 50 years, again, we are so excited about the geothermal, and we are trying to investigate that. Okay. Okay. And the idea is basically coming from the climate change and the global warming. This is something that attracts lots of attention these days. And if you were aware, there was a COP28 just a couple of months ago, which most of the countries, they came together in UAE, and they were discussing on the policies and how to deal with climate change. Okay. And when we are talking about the climate change and the global warming, we try to find a relationship of that with the CO2 emissions. We will go to that discussion. We'll see why that is important. So the major motivation behind these studies, the recent projects, recent investments in other sources of energies like geothermal, wind, solar, is coming from our interest in somehow mitigating this global warming. Okay. And to see the impact of the global warming, where it comes from, why we should do the energy transition. What does it have to do with the energy? So it's good to just step back and see the documentations and also the discussions around the global warming. The first thing that comes is, do we believe in global warming? Because still there are people that they are not believing in global warming. What they were saying is, if you look at the whole geological time frame, there were times that we had, temperature of the earth going high and or going low, and these are basically the cycles of the weather change that we will see. But now, because we are looking at a very specific time, which is very little in compared to the geological time, we're thinking that's a huge problem. So there are discussions around it. So we wanted to see the facts, see if this is something that's real. And if we search through it, if we look at the documentations, we actually see that it's proven that there is a global warming, actually. And this whole thing started after the Industrial Revolution, around, let's say, 1880s. And after that, by coming to the era of the Industrial Revolution, we start intervening more with what we call natural carbon cycle of the world. And by that, what I mean is we start producing more CO2 and more other greenhouse gases, which in this graph, which is coming from the EIA investigation, I'll show you more discussion on that. We are looking at the Earth average land and ocean surface temperature, okay? And we are comparing that with basically the average of the temperature from 1880s to 2021, okay? So at every year, we are comparing that average temperature of the yearly with the average temperature from 1880s to 2021. So the blues were showing that those years, they had a lower temperature in compared to the average of the temperature of the whole time span. But we can see that, especially after 1991, this increase in the temperature, global warming, is accelerated, and we have lots of years with the temperature much above the average temperature. And when we're talking about much above the average temperature, we're not talking about tens of degrees of Celsius. Okay, the average temperature has increased by around 1.04 degrees Celsius. Let's say 1 degree Celsius compared to pre-industrial era, okay? So when we're talking about the change in the temperature, we heard it talking about that. And then the whole goal of the climate change, let's say Paris Agreement or COP28, is to keep that temperature rise below 2 degrees Celsius, preferentially below 1.5 degrees Celsius. Why this is important? Because we know most of the Earth's surface is covered with water. And to warm up that water, you need to expose huge amount of energy. Okay. If you remember, we define the energy like a BTU as a 1 BTU to be equal to the temperature required to increase the 1 cubic feet of water by 1 degree Fahrenheit. Now, considering the volume of the water in the oceans, you can come up with how much energy has been stored in the sea oceans to increase that temperature by 1 degree Celsius. This temperature rise has led to seawater to rise by 8.8 centimeter. Okay. And more than 51% of the icebergs to melt. So even though we're talking about 1 degree Celsius, the impact is huge. Okay. So we have measured those. We have measured the amount of CO2 and the greenhouse gases that we are emitting per year, and we are comparing those with the climate change and the sea level rise and the temperature. And we have documented all these, which basically shows this direct relationship. But all these greenhouse gas emissions are not just the CO2, okay? There are F gases, fluorine gases, there are methane, there are CO2 coming from the land use, and there are nitrous oxide, and all these basically are contributing to the greenhouse gas emissions. However, if you look at the proportionality of the contribution of different gases, the CO2 that's been emitted from the fossil fuels, let's say in 2010, takes 65% of the greenhouse gas emissions. Again, one thing that we need to pay attention is even, let's say, the F gases, they take 2%, or even if methane takes 16%, the relationship is not linear. The impact of F gases or methane gases on greenhouse, on the global warming is much worse than the carbon or CO2. So this 16% might be equal to, let's say, 30% or 25% of the CO2 emissions. Okay, so the relationship is not linear, but just to look and to find the most guilty gas resulted in the global warming, we can point to carbon dioxide from the fossil fuels. Okay, so we have a global warming. We have evidence that proves that. And then we see this global warming is mainly due to presence of the greenhouse gas emissions and mainly carbon dioxide that comes from the fossil fuels. So the idea is if we can cut this, then we can have a much better control on the global warming, okay? And then obviously then we're gonna go through work with the methane, and we're gonna go and work with the other greenhouse gases as well. But for now, the majority is assumed to come from the CO2. We have to prove that, and we also looked at the temperature change from the pre-industrial as a function of the cumulative CO2 emissions in the world. And we can see that this black line actually shows that the cumulative amount of CO2 emission since 1850s. And this shows the temperature rise at the surface. We can see this direct relationship between the CO2 emission and the temperature increase. And after this point, which is 2020, the rest is predictions. So there are so many different predictions that different agencies has done, and then they were expecting with how much more CO2, how much more temperature will rise. Okay, and based on the Paris Agreement in 2016-17, in the COP, what we are trying to do is we are trying to limit this rise of temperature to 2 degrees C. So if I look at the 2 degrees C as my limit, I don't want to go above that. And then I draw a line and come here to any one of these forecasts, I can come up with the maximum amount of CO2 that we are allowed to send to the atmosphere. How much we have already done, this is the amount that we have already emitted. Let's say 2,500, okay, and gigatons of CO2. And how much needs to get to that 2 degree? Let's say 3,500. For example, let's say we have 100,000 gigatons of the CO2 left. So this is a kind of a methodology and a mentality to work with the CO2 emissions. So we have some credits on the CO2, but we don't want to go above that. The next question comes, why even we use the fossil fuels? And the answer is obviously we need energy. And this graph shows how the energy demand has been increased, energy consumption has been increased since 80s, okay, since 1800s. And as you can see, the amount of energy that we are using has been increased significantly. And most of that is generated through the application of oil, gas, and coal, okay? So the reality is we need energy. We need energy to develop our countries. Where the energy comes from, majority of that is come from oil, gas, and coal, from fossil fuels. But burning those fossil fuels will lead to CO2 emission, would lead to the global warming. So the idea is to reverse this process, to decrease the amount of fossil fuel and decrease the CO2. But there's a problem. We still need to generate this energy, right? Because we need that for our countries to develop, and we have some comfort of living that basically we want to keep it, and we want to actually increase that comfort. We don't want to go back to many years ago. Let's say one can say, okay, let's go to bed at 7 o'clock p.m. and turn off all the lights. Then there would be a huge saving on the energy. Then you might cut those a huge amount of CO2 emissions, but that's not practical and that's not possible. We are not going to erase the problem. We have to come up with a technology to solve the problem. So these are all past till now, right? So what about now to the future? There are two agencies, IEA and EIA. These two agencies are international energy agencies, which are looking at the whole energy landscape. They're looking at the policies, they're looking at the wars, developments, governments, and they come up with the predictions. So considering all these developments and promises that the countries are giving in the agreements like Paris Agreement or COP28, these agencies, they have made the predictions, right? And the predictions are that the actually using energy is not going to decline. We are actually will increase the energy consumption by 50% in 2050. Okay, so we need energy, and we will continue to need energy, and not in the same pace. And actually, we are going to increase that use. Majority of that is industrial application, transportation, residential, and some commercial. They have also did the predictions on every sector of the energy. And they're showing that even every sector seems to need more energy, okay? So where these energies are coming from? Again, majority of them are coming from the oil. And actually the predictions are also that the energy that will come from the petroleum will increase by 40% in 2050. Again, all these considers that all the policies that we are making for energy transitions stay valid, right? We know, like when the US entered the Paris Agreement, with the change of the government, US came out of the Paris Agreement. You know, when we had different government, the first day president said, we don't want to be in the Paris Agreement, so we are out of it. And then with the Biden administration, we entered the agreement again. So there are changes that might happen, but let's assume that those changes are not gonna happen, and we are going to keep our promises on energy transition. And even if we do that, still the projection is we will need 40% of energy coming from the oil and gas. The good thing, we are increasing the renewables. See, we are expecting 75% increase in the renewable energies by 2050, but it's still the amount of energy that we are producing from the renewables is much less than what we are producing from the oil and gas and coal. Okay, so again, this is another graph which basically represents the same idea, showing the portion of the energy produced from every one of these sectors, from one of these resources. Like in 2020, renewables provide 13% of our energy. 27% coal, 31% oil, 25% natural gas, and 4% nuclear. Going to 2050, the expectation is, or predictions is, that 13% increases to 27%, okay? By looking at the solar, looking at the wind, looking at the hydrothermal, looking at the geothermal, looking at all the renewable PVs and energies that we are using. But it's still 28% oil, almost 20% coal, 23% natural gas. Add them up, we're almost having 70% of the energy requirement still from the fossil fuels. Okay, so this basically brings us to the idea of which energy source is the best. And obviously, with all these discussions, we'll see that steel, oil, natural gas, and coal will continue to serve as the primary energy source for the future. But obviously, we need to look at the renewables, and we need to increase the share of those. When we're looking at these different energy resources, there are four major topics that we need to look: cost, storage, scalability, and environmental impact. Okay, so if we look at the cost, generally what you're talking about the capital expenditures, capex, how much money we need to put in front to develop this technology. OPEX, how much money we need for operating and maintaining these facilities, and the fuel prices. Okay, there are two concepts that have been used to compare these different energy sources to make a comparison between apple and apple. Okay, one concept is called the levelized cost of energy, or LCOE. Okay, so the LCOE is basically a total life cost of the technology. Let's say one technology has 20 years of the life, like solar, right? Solar panels, they have 20 years life cycle. Or windmills, they have 20 years life cycle. So how much money you invest in that 20 years of development of that technology divided by the total lifetime energy that you can produce from that technology. That's called LCOE. LCOS is the same. It's like how much money you have to invest for storing that energy through the life of the technology, divided by how much energy that you can produce or you can store in that storage. So LCOE and LCOS tries to normalize all these costs such that we can compare these different technologies. And there's one additional parameter, which is basically federal tax credits. There's a whole discussion on the carbon tax, taxation, different regulations on that. But there are production tax credit and there are investment tax credit, which is basically the money that the government pays back if we spend on these kind of technologies. So here is a brief comparison between all these renewable resources that we have and the natural gas, obviously. So what we have is dispatchable technologies, resource constraint technologies, and capacity resource technologies. So what is dispatchable technologies? Dispatchable technologies in the layman languages are the technologies that they have a switch. You can turn it on when you need it. You can turn it off when you don't need it, right? Like a natural gas, right? You wanted to use it, you turn it on. You don't want it, you turn off the well. You know, the production and the supply is on your hand. You can produce it when you wanted to produce it, how much you wanted to produce it. You turn off the valve, you drop the production. You turn it on, you open the production. But the same goes to the geothermal, right? The same goes to the nuclear. But the technologies like wind, right? These are not dispatchable. These are called resource constraint technologies. You don't have any control on the wind. You don't know how much wind you will have and how much energy you will produce, or the solar. Like if there's no sun, if it's night, obviously you don't have the solar energy, right? So these are constraints. And there are some technologies that we use to just kind of meet the demand, right? If there is a peak in energy use that we need to catch it, we are going to use the combustion turbines and battery storages, okay? So these different technologies, they have what they call capacity factor. So what is that? It simply defines out of 100% capacity of that technology, how much of that we can use, okay, or we are using. Basically, the combustion turbine, we are just using 10% capacity, which means we are just using temporary. This is designed for temporary applications, not for full applications. The solar, let's say it's like 29%, which means basically you're using 29% of that 100% capacity, okay? And then when you compare all these costs, capital, operational costs, you come up with a total LCOE and LCOS. You will see that between all these different cases, the solar standalone turns out to be the cheapest. However, the much lower capacity of 29%. After that, what you have is the geothermal and the natural gas. But these two, geothermal and natural gas, even though they have similar, very similar LCOE, they have much higher capacity factor that can be used, okay? So that's why we picked on the geothermal. So that's how the interest on the geothermal is coming up, okay? So we wanted to do the transition, we wanted to cut that. We need to have a reliable source of energy because as we said, the energy demand will increasing, right? And we need to answer that demand. So geothermal is one of those things, which basically has a good storage capacity, you know, using wind, solar, you need to have large batteries. Again, even though these are good sources because they are scalable, you can do it for any different amount that you want. You can generate it for your cell phone, like a storage battery for a cell phone, or for your desktop, or for your house, or for your town. So it's very scalable, but the storage is a problem, you know, how big those batteries will be and all that. But the geothermal is like natural gas. We are using formations. We are using depleted oil and gas reservoirs. We are using the sandstones that we have been using before. Now we are using it to store the geothermal energy. I already talked about the scalability. So basically the scalability is, as I said, the energy needs to be scalable. Like geothermal has a limitation, right? It's location specific. In some locations, you don't have the thermal gradient to generate the geothermal, okay? But the batteries, they don't have this issue. And finally, environmental impact and concern of these. And every one of these technologies, they have their own. But the environmental concern is not just limited to the CO2 emissions. It includes the land use, right? It includes the potential for habitat destruction, or biodiversity loss, or all these changes that we are doing to our planet can also cause some environmental issues, okay? So when we're talking about the environmental issue, it's not just the CO2 emission, and we have to look at the other ones. I'm picking on two because these are the things that we don't regularly see or hear from the news. Everybody's talking about the solar panels, application of the solar panels. Put the solar panels here on the top of your house and here and there, generating the large scale solar farms like this. But I'm not sure if we can safely defend the land use and change in the habitats and the diversity that these solar panels or solar farms are generating. This beautiful scenery before installing all these solar panels look different, but now it's all lines of solar panels which are basically made of metals, toxic materials such as gallium, tellurium, silver, and if something goes wrong, which has been, this picture is coming from the solar farm in Puerto Rico. Just Google it after the hurricane. And then this is basically what you will end up with. All these heavy metals, all these destructions right at the surface. And this has been actually be involved with the heavy rainfall, which basically takes all these materials, all these toxic heavy metals right in your water sources. Okay. This is something that we are not discussing. Look at the land footprint. Look at the amount of pollution that we're going to do with this. Just putting aside where all these heavy metals to build these solar panels coming at the first place. We don't talk about the mining issues and mining these, extracting these heavy metals, processing and the building these, which again requires energy, which most probably comes from the fossil fuels. So there are things like this that when we are talking about the energy transition, we need to pay attention. And it's not just jumping into the discussion of energy transition without knowing the background, without knowing the energy requirement and energy demand of the world, and without looking at other problems, other environmental issues. We don't want to cut the suit and get into other problems like these, okay? So we have to come up with a solution that solve all our environmental concerns. This is another one. This is basically a San Giorgio Pass wind farm, okay? So again, the scenery completely gone. Obviously, the habitat is significantly destroyed and changed. The number of the birds that were killed by these wind farms in the order of billions. But the argument against that is, hey, you are killing billions of birds with the regular transportation. But come on, is that really justifies killing another billions of birds with the wind mills, which is again another type of discussions. And again, these ones, the blades, the wind blades, they're all coming made of heavy metals. It's very big. Even when you wanted to transport it, you have to cut it. They're even bigger than Boeing 747 wing. So these are the problems. And after 20 years, and if they break, what happens to them? Okay, they have been buried. Where? In a landfill, not in California. This is in Wyoming. Okay. So the same windmills has been transported and dumped in the Wyoming. This is again coming from Bloomberg, and there's a YouTube channel on that. We can just go and look at it and see shallow, just burying all these, and you can imagine a rainfall and moving all these metals and toxic materials to the water sources. Okay, so there are so many things around the other sources that's not been discussed. So here we are trying to open up the discussion and just make sure that we know all the other resources. And if we have limited funding, limited capacity, we wanted to find the best way and best place to spend that. So that's basically where it comes from. The other discussion around the energy transition is ethical aspect of it. So this is a very funny and very interesting graph. This basically shows the energy consumption per capita in different countries in Africa. Okay, so this is the energy consumption per capita for a year. Okay, it's an annual energy consumption. So one person in Ethiopia or in Ghana is consuming 300, let's say, kilowatt hour per year. My refrigerator, with all the energy efficiencies, is using 459 kilowatt hour. So when we're talking about going and leaving the fossil fuels under the ground, okay, not using it for the development, to bringing these many peoples that they are on the energy poverty, out of the energy poverty, such that they can also have a life that similar to the ones that we have, is basically raising a very important ethical concern. So this is again another thing that we need to think about: how billions of people, they don't have access to the clean cooking, billions of people, they don't have access to the clean energy, to the energy, and we are talking about eliminating the cheap, easy, and the fast energy that can be delivered to these people. So these are the discussions around this. But what is the conclusion? The conclusion is we're going to use the oil and gas, we're going to use the fossil fuels because of our energy demand, and the renewables with all these forecasts cannot meet the demand. So one thing that we need to do is carbon capture and sequestration. You know, carbon capture, pre-combustion, post-combustion, using different technologies like oxyfuel, and trying to meet that net zero CO2 emission. And the other way is also to invest our limited capacity on a renewable energy that has a higher capacity and better promises, like geothermal. Okay, it was a extensive 40 minutes long discussion, but I thought that might be required before delving into the geothermal energy and earth heat discussions. Okay. So coming to our discussion of the geothermal energy. So now, if we say that the geothermal is promising in terms of the cost, LCOE, LCOS calculations that we showed, and in terms of the capacity and all that, there's a question. Then basically, what is the geothermal system? Okay. And what do we need to do? Where the investment should go? Okay. So what I will try to do is to, in this week discussions today and Thursday, cover the basics of the geothermal, go over all the terms and the terminology that we are using in the geothermal. And then next week, delve into more details of the completion, drilling, completion, production, stimulation, and the energy production. Okay, so bear with me. Geothermal systems, we have different type of those. We have what we call traditional or conventional geothermal systems. These traditional or conventional geothermal systems are basically mainly are related to activities which resulted in energy or heat production from volcanic areas, or areas which are connected to volcanic areas through highly naturally fractured systems. Okay, and how are we going to extract this? Generally, in the traditional geothermal systems, or what they call conventional geothermal systems, we are trying to extract the heat from the heated aquifers. Okay, so there's an underground water system, okay, or aquifers, which due to the volcanic activities gets really warm and hot. So it's going to be a hot water aquifer, or in some cases even converted to the steam. So we are going to extract that hot water or steam from the aquifers and then use that to run the turbines and to generate the electricity. Okay, that's one way of doing it. In the traditional or geothermal or conventional geothermal, The major mechanism is convection. Okay. So what is convection? Convection is associated with the fluid flow, right? Fluid moving from one point to the other point. So you should have a movement of flow in that system. Hot water that we are producing from this aquifers, hot aquifers, comes to the surface, runs the turbine by changing in the pressure, and then it gets cooled down, and then it sends back to the aquifer to warm up and then reproduce again. So it's like a cycle of production and injection of the fluid to these hot aquifers. Okay. The second type of geothermal systems is called closed loop, okay, or some called ground source heat pump, GSHP sources, okay. So what is the closed loop? Again, in the case of closed loop system, we are still talking about areas with the extremely high temperature gradient, like volcanic areas, or the areas connected to the volcanic areas, very close to those areas with a very high temperature gradient. Okay, but in the closed loop system, the mechanism is different. Okay, we are not talking about convection. Okay, there's no fluid getting into the formation, warming up, and coming back to the wellbore. Okay, so what we are talking about is to have a wellbore drilled in the formation and circulating the water or circulating what we call working fluid into the wellbore. That working fluid could go from the could be injected from the annulus to the casing, and as it goes down, it could get warmed up by the temperature gradient from the formation, and then producing that back from the tubing. Okay, or it could be injected through the tubing and then produced back through the casing, depending on what kind of fluid that we are using, what kind of fluid that we are injecting, okay, into the formation. Again, these kind of systems and these kind of systems, we are not injecting the fluid into the formation, okay? We are trying to get these fluid, these heat out of the formation through what we call conduction, okay? So there is no convection, there's not fluid flow, there's a conduction, there's a heat transfer from the formation to the working fluid. These closed loop systems could be shallow, in the order of tens of feet, 4 feet, 8 feet, 10 feet, 20 feet, 40 feet, 200 feet, or it could be in the order of 10,000s of feet, deep closed loop systems, okay, which we'll go over the discussion of both of those, okay. And then what we have is called the third system is enhanced geothermal or engineered geothermal system, or what is called in the industry hot dry rock system. Okay, so what is that? In this case, we are not talking about the huge temperature gradients. We are not talking about the volcanic areas. We are talking about any area that has a good temperature gradient. Like here in Morgantown, West Virginia, we are in Appalachian Basin, we are in the sedimentary rocks, we are far away any volcanic activities. But simply by drilling a deep well and monitoring the temperature gradient, we can reach to the temperature that can be used for a specific purpose, which is basically in our case, heating and cooling of the university. Okay, so in the case of enhanced geothermal system or engineered geothermal system, we are not specifically looking at the volcanic areas. This can be done anywhere, but we just need to make sure that we do have the temperature gradient, and then we drill as deep as required to get to that specific temperature. But this technique, like the traditional technique, requires a convection, requires us to inject water to the formation, let the water heat up, and then produce the heated water. okay, and then use the heated water. This can be done in different ways. You can have 2 vertical wells and then frack the vertical wells, because as I said, these are going to be deep wells. And when we're talking about deep wells, then most probably we will not have enough porosity, enough permeability in those rocks. So what we need to do is to perform hydraulic fracturing, okay, or frac stimulation, where what is that? Which basically we are injecting water, we break the formation, and then we send sand. And for the geothermal, it has to be a different kind of sand, which should have a higher thermal conductivity, and also avoid the loss of the energy, thermal energy, when we are passing the fluid through these sand packs. And also, we also need to make sure that we will not have problems like the sand production, because this is different than the regular fracking that we are doing. In this case, a closed loop system, we keep the fractures open for the fluid to go. In the conventional fracking, when you frack, you start doing the flow back, so the formation closes the fracture and holds the proppants in place. In this case, we are not going to do that. We are going to have a closed loop continuous injection, and that requires the fractures to be open. So we need to somehow make sure we hold the proppants in place. So these are the discussions. These are more detailed discussions that will go when we will discuss the completion designs next week, but just the heads up. Or what we can do is we can drill 2 horizontal wells, okay, and then inject from one and then produce from the other one. Again, these horizontal wells needs to be connected through the fracking, to generating the hydraulic fractures. So this is called engineered geothermal system or enhanced geothermal system. There are techniques that's been discussed. Sage is basically one of those companies in Texas is promoting this. They're talking, and they have their own pilot. They tested. They're looking at the technique very similar to what we do in oil and gas industry in a steam stimulation, in the cyclic steam stimulation, or what we call huff and puff. In the heavy oil reservoirs, we inject steam, we shut the well, we let the steam to soak into the formation, heat up the formation, drop the viscosity of the oil, and then we open the well and we produce. Same concept. They try to inject the water through the well bore, and then let the water to soak into the formation, increase the reservoir pressure, and then they open, when it's warmed up, they open the well, and then they produce. So again, this could be on a single vertical well, or it could be on a lateral wells. But what they're doing in this case, because this is a single well operation, they are doing it in a multiple single wells. So they are working like a pistons. One well is injecting, the other well is producing. So this way they keep the continuous flow of the energy from these geothermal sources. Because remember, in the case of geothermal system, we said we wanted to have a switch button. We wanted to make sure that we have energy when we want it, and we can store it when we don't want it. So if you just go by a single well, while you are waiting for that water to produce, you don't have any energy production. But if you have multiple wells, then you can do these in sequences. You can have some wells injecting, some wells producing, and then you can change this. Coming to the applications, there are 2 different applications. In general, there is a direct use application, and there's an electricity generation. We need to make sure that which one of the applications we are looking for. For the case of the West Virginia project, we are looking at a direct use, which means we are going to use the heat that we are harvesting from the well to heating and cooling of the buildings. It can be used for greenhouses. It can be used for aquaculture ponds, or industrial purposes, or drying crops, and those kind of facilities, okay? And in this case, basically, what we are doing, we are not using that heat to generate the electricity, okay? The direct use is there is no heat exchanger. Okay, there is a heat exchanger. There is no heat conversion process. Okay, so we are not converting the heat to the electricity. Okay, in the case of the direct use. In the case of electricity generation, which is basically mostly comes from the conventional geothermal power plants, we are generating electricity through heat conversion processes. Okay, we are taking the water or steam and we ran it through the turbines to generate the electricity. So there would be two different applications, either the direct application or electricity generation. So these are the two major applications that we have. The direct use of the geothermal system has a history. As I said, it has a long history, and there are different forms or the systems that can be used for the direct use. We can use the hydrothermal. There are identified hydrothermal resources from 2010 to 2015. There are some undiscovered hydrothermal resources that we are looking from 2020, and we are expecting to recover and find more by 2050. There are systems like closed loop heat systems, which are near hydrothermal systems. These are, again, the systems that we are using to produce the energy. And obviously, deep enhanced geothermal systems. These are also the ones that's been expected to grow significantly in coming years to meet the energy demand and also the applications. This graph is also very interesting because it basically shows the temperature range and the application. Basically, when we are working with the water, hot water, or when we are working with the steam. Okay, and if you're working with hot water, with what kind of temperatures we're talking? Like if your hot water temperature can raise to 20 to 40 degrees C, then basically we have some residential applications like warming up the pools. If you have a system that can produce hot water with 40 to 60 degrees Fahrenheit, 40 to 60 degrees Celsius, then in addition to the residential applications, you can have some commercial or industrial applications too, which basically making that heating and cooling of the universities or different industries. And if you can take it to 60 to 80, then basically this can also be used for different systems for residential, commercial, in air conditioning, for example. As your temperature goes up, you can use it for more and more applications for refrigeration, for example, if you can have a temperature of 100 degrees C. If you go in terms of the steam, then you also have a huge range of applications in the industry sector for that temperature range. So what we are looking is, depending on the geothermal gradient of the location that we are, depending on the depth required to reach to that temperature, and depending on the efficiencies of this heat transfer, we can look and see how much of the temperature we can provide at the surface, and then what is the application for that. In terms of energy conversion process, there are two types of energy conversion process. There is a binary organic Rankine cycle and flash. So when we're talking about the binary plants using the heat exchanger, this is for the cases that the temperature is below 200 degrees Celsius, okay? When the temperature that we are producing is below the 200 degrees Celsius, we need to have a heat exchanger, and we need to have a secondary working fluid, which generally has a much lower boiling point than water. So we are transferring the heat from the water to that working fluid, which has a boiling temperature less than water, and then we use that to generate the energy. So that's basically when we are using the binary heat exchangers. In the flash plants, this is basically that we don't have the secondary fluid involved. This is where the temperature is already above 200 degrees Celsius, and this high temperature can lead to simple generation of the energy in the turbines, okay? So binary and a flash. And then EGS and geothermal systems also divided in the three categories. One would be hydrothermal, as we said, that traditional or conventional one, which we were trying to extract the heat from the aquifers, hot aquifers or steams. Near hydrothermal field or NFEGS, these are those closed loop geothermal systems, and the deep EGS, which are basically the deep wells that we are drilling and we require to perform the hydraulic fracturing to extract the energy. Each one of these, hydrothermal, near hydrothermal, or deep, depending on the temperature of the fluid that they can provide at the surface, they could be either binary or flash. So again, every one of these will be divided to hydrothermal binary, hydrothermal flash, near hydrothermal binary, near hydrothermal flash, deep binary, deep flash, depending on the temperature that's been provided at the surface. Looking at the annual technology baseline, we can see that the hydrothermals, the number of sites that they're producing and their temperature is above 200 degrees C is 21 sites already active. We have other sites like 23, 17, and 59, which are operating at temperatures below 200 degrees Celsius. So 21 hydrothermal flash, and the rest would be hydrothermal binary geothermal systems. These are important because when you are designing and when you are looking for the geothermal energy, we first need to define your demand, how much energy you need for what application. Is it a direct or is it a electricity generation? If it's a direct use, what is the application? What's the range of temperature that you need at the surface? And then you go and you look at where you are located, and then you see if you can use the hydrothermal. If you are, let's say, in California, that you have lots of applications, lots of accessibility to the hydrothermal, or no, you are in Appalachian Basin and you need to go for the deep EGS systems, okay? So, and then when you wanted to go there, you need to look at the temperature gradient of your field or where you're located and see how deep you need to drill to reach to how much of the temperature, and then go based on that. So these are basically the basics and the baselines that's required to come up with this. I think I'm right at that 1 hour. So I'll stop here, and we'll continue these discussions on the hydrothermal, closed loop, enhanced geothermal systems on Thursday. And then next week, we go more into the specific projects and specific applications. And thank you. If you have any question, I would be happy to answer. And please indicate that question in the chat room.
Dr. Ibrahim, thank you very much. Please, if for the audience, if you have any question, please write it down in the Q&A section. We'll give you like a minute. If you have any question related to the topic of today, please write it down in the Q&A section, not in the chat. Write it in the Q&A section. Thursday, we will meet again the same time, and we will meet next week, Tuesday and Thursday, the same time. So, Dr. Ibrahim, I believe we have some questions in the Q&A. If you start reading, answer them, this would be appreciated.
Okay. Okay, so Morgan is asking about how the fracking of the hydrothermal reservoirs is different than the fracking in oil and gas. That's one of our discussions for the next week when we are talking about the enhanced geothermal systems. But for now, to just know, generally there are different concerns In the oil and gas industry, when we are fracking, as I said, we are just opening the fracture, putting the sand between the fracture, and then we are producing, and the overburden pressure will close the fractures. We are actually putting the sands because we don't want the fracture to completely close up, and we wanted to have some production, some permeability left in the hydraulic fracture. But the overburden pressure keeps the proppants in place, and actually sometimes it actually crashes them and it makes some proppant embedment in the formation. But in the case of geothermal, you have two wells that you want these two wells to communicate. So you wanted to inject fluid from one well, and then the fluid's supposed to pass through the fracking, go to the other well, and be produced. So you actually keep the reservoir pressure high. You don't let the reservoir pressure to go down to close these fractures. So so this is basically that. And then there are different techniques to do that. Like more advanced techniques is coming with what we call in situ proppants. We can use some polymers. These are very advanced technologies that they inject polymer. Okay, and when that polymer goes to the wellbore and gets to that high pressure and temperature, it gets activated and it starts generating solid. So you are basically, it's like sedimentary rocks. It's like you are doing chemical sediments. It's like you are injecting the fluid, and then when the fluid, which is polymer, gets to the right pressure and temperature, it starts crystallizing. And when it crystallizes, it basically generates a bulk system with the porosity and the permeability. And in that case, you can actually work with the polymers, which they have good thermal conductivity, such that you don't lose the temperature. Because one of the major concerns in this area is you limit the amount of temperature heat loss through these formations. And the other discussions we will go over it, the cementing and all that needs to be very specific to avoid that heat loss. This is a very good question. Thank you for bringing that up, but we will get to that most probably next week. Is there any relationship? Mohammed is asking, is there any relationship between depth and temperature? Yeah, there's a temperature gradient again, but this is very different on where you are located. So generally, you can say like 1 degree per 100 feet, 1 degree Fahrenheit per 100 feet, but not like you could have different temperature gradients. We will show you basically. Let me just really quickly go to here. Okay, so this is basically the temperature gradient map, right? It shows, for example, the temperature at 5.5 kilometers in the United States. Like what is the temperature? So you can see that the temperature is not the same at the same depth in different locations. We are located in West Virginia right here, which we see this higher temperature. That's why we are tapping to the geothermal here. If you were like somewhere here, obviously we couldn't do that, right? Or if you are in the California, right? If you are here, then basically you have access to these volcanics area, and then you can produce more. So there is a relationship, but that temperature depth relationship is not very simple. It has a relationship with deformation as well. So as you go down the ground, you might have sandstones, you might have clays, shale, you might have limestones, carbonates, gypsum. So depending on what type of formation you have, the temperature gradient within that formation is different too. So we will do those by performing the well logging and then the temperature logging. We come up with the formations and the temperature, and we correlate those. I'll show you exactly the same discussions and the same temperature, and we will all show you why most of even these temperatures temperature gradients, especially in these areas, are underestimated. And this is again very good question that we will touch on that next week. Okay.
So, do you still have any other questions?
Yeah. So one of the slides mentions that the geothermal, again, Morgan is asking, can be used to dry clothes with the 200 degrees C. How does this work, or is this temperature required for turbine? Yeah, generally, when you go above like 200 degrees Celsius, then you use that to generate the electricity, and that's basically one of the applications again. And you can use that for that. But in the case of direct use, yes, you can just use it as a steam, right? You have a very high temperature, and then you use that in a commercial sense for drying, not obviously for the for the local, for the smallest scale. So that amount of temperature is far beyond the application for the small scale use. Okay, any other question? How could better geothermal generation technologies be developed in geological formations with complex heterogeneities associated with the hydrocarbon deposition and mineral bodies? How could better geothermal generation technologies be developed in geological formations? Yeah, basically we need to perform a really extensive studies like what we are doing here. It's not just the petroleum engineering job. We have a big team involved geology, involved petroleum, involved chemical engineering and mechanical engineering to work with this. Specifically for the reservoirs with a high heterogeneity, we are talking about a variation in the mineral content, right? So if you have a high heterogeneity, it means you have variation in the mineral content, that we can come up with a good idea of using XRD, XRF. If you have the lithoscanner log, you can also get the idea from that. So understanding of what type of reservoir rock properties you have in terms of the mineralogy, and also the fluid samples, like what type of minerals, anions, cations you have in the fluid, in the water of your formation. You need to come up with those two. And then when you have that information, which I will show you we do for this specific field, then you have to perform studies like in the geology department. We are looking at the isotopes. We are looking at the reaction between the fluid and the rock in this geothermal. When you're exposing the water that you're injecting, which has a completely different chemicals, with the formation water, which has completely different chemicals, what will happen in terms of the precipitation of the minerals, scaling? So those are the things that we need to investigate. So, and we do so to be able to understand the effect of heterogeneity in terms of the mineral content, heterogeneity in terms of the fluid properties, heterogeneity in terms of the fractures. Like we are looking at one of the major things that we are looking is the natural fracture distributions, right? That generates a lot of heterogeneity in the formation. And we come up with that by looking at the FMI logs, drilling acceleration data, looking at the microseismic activities and all of that. So it's a very complex and multi-phases project, which basically we are looking at every aspect of this. But again, the geosciences, petroleum engineers, and the geologists, these are the best people that can also involve in energy transition. This is what we are doing. Like the drilling would be very similar. The completion would be very similar. The modeling would be very similar. We have been using this. We have used the huff and puff techniques. We have used the multi-wells, horizontal well drilling in SAGD, in WAPACs, in the enhanced shale gas recoveries and stuff like that. So, but how to better perform this is requiring us to work more closely with the geologists, geochemists, and other fields of engineering, and also develop our understanding and use that for the advancement. Like one of the major problems that we saw, like for the geothermal, you have to go to 15,000 feet, 16,000 feet. So you have to start with a much bigger wells at the surface. So your well, your surface casing, intermediate casing, these are going to be much bigger than the conventional wells that we have been using. So if you have a bigger well, then the coring of that well, logging of that well, it basically brings more and more complexity. But we are well positioned to tackle this, but requires gathering a good amount of information and looking at this. But regarding the heterogeneity, what it comes to mind is looking at the mineral, fluid, natural fractures, and quantifying those and see how they will change as a function of pressure and also the temperature. Because the pressure, as you're injecting, you are building the pressure, you open up the fractures and stuff like that. And reaction would be different at different pressure and temperature for different composition of fluid and the mineral. I hope I answer your question. Okay, if we don't have any other question, hopefully see you guys on Thursday.
Dr. Ebrahim, thank you very much. For sure, we'll see you again Thursday at the same time.
Yes, thank you.
Thank you.
Bye-bye.
Thank you.